with the parallel programming lecture. And notice here that I will talk about the very basics of parallel programming, and I don't expect you to be expert, right? After this lecture is just the basics, and I would say the concepts that you can learn, right? From the very basics of the parallel programming, right? And also some tools from Matlab that can help you. I mentioned some of them in my previous lecture. So here I start with a definition of what is parallel programming. And here is I wrote this design of art of writing the code that execute tasks on different computing units, cores. Notice here the nomenclature, cores. This is a word that we have seen previously during this course. And the key word here is simultaneously, right? So all the tasks that will be executed will be done executed simultaneously. So currently the CPUs are shipped with several cores, right? And for instance, here in this machine that I am using, I can see that I have several cores, right? And that's why I can run different applications without experiencing delays as previously in the 80s or 70s, right? When one opened some application and then it took longer for the other applications to complete. So in principle, on this machine that I am using in my laptop, I can run a parallel program, right? But if I want to go beyond the number of cores that I have here in this machine, then it's a good idea to use one of our HPC clusters. Yeah. So here I wrote two of the most common programming models. One of them is called shared memory. And when I talk about SPMD in Matlab, I mentioned the shared memory programming model. And this is the way it works. We have several cores. Here I just depicted two of them. And the point with shared memory is that the cores can share the same memory space, and because of that, they can take advantage of the high bandwidth. Yeah, so it doesn't cost so much to get the data from one of the cores to the other. Yeah? So, but this programming model is limited to the number of cores that share the same memory. And in particular, for instance, on NAISS, we have some nodes that can share that have cores, 128 cores that can share the same memory space. But if you want to go beyond this number of cores, then you need to use a different approach. And here I mentioned one of them, which is called distributed memory. And the difference here is that the cores don't share memory, yes, but they can exchange the data by using some protocol, yes, for transferring messages across each other. However, the novel architectures are more complicated than this, distributed or shared memory, because in principle, some cores can already share some kind of memory and at the same time pass messages across some network, yes, by using some protocol. So this is a the standard node on Kebnekaise, and here you can see how the number of cores, in this case 28, are sharing some memory within a node. So why is parallel programming needed? So you write your Matlab script. For instance, we mentioned previously a for loop, plain for loop, and then you run it. Even if you have a big cluster as our clusters, right? Which have several computing nodes and many cores. So you will be using one single core. Yeah. So if you want to run or and use this computing power, then you need to write your code so that it is aware of the other cores and also the network communication. So once you write your code, right, and you start using the parallel computing, so there could be some issues, right, such as underusing or overusing the resources. And we have seen previously, right, that you can start your job. Here I show you one example for the parallel code that I wrote previously. And here you can request a number of cores, right? But then you can underuse the cluster. For instance, if you have less iterations here, or if you have even more iterations, right? So this is one way to underuse or overuse. And this can cause issues on the cluster, but this come after you start using the parallel computing capabilities. So we have some tools in our centers, and here I like this tool from HPC2N, and there are other tools in the other centers. For instance, at the other centers, one has uh, the option of using interactive sessions, right? Where one can do an SSH to the nodes, and then one can use the top or htop commands and see if the resources that one allocates are being used properly, right? Imagine that you request 10 cores, but your simulation is using only one, right? So this tool at HPC2N is very useful. It gives you the statistics in a graphical manner. And here I put one simple case on how to use that. And you can take a look at it. So in Matlab, I mentioned previously some options to parallelize your code, right? And here I mentioned one of them. This is called threaded programming. And when I use the word SPMD in Matlab, I was referring to this threaded programming where one is sharing the memory across the different workers. So notice here that there are also some linear algebra packages, for instance, LabPack BLAS, that can be used inside the codes in Matlab. For instance, when we are solving some matrix operation, so one could use one of these libraries. So in order to activate the parallelization mode, One uses some variable like this one, OpenMP number of threads. And in that case, you can use another parallelization level besides SPMD that is proper from Matlab. What one can use an implicit library for parallelizing your code. And that's why I included the words underusing or overusing the cluster, which is essential when you are parallelizing your code. And this can be confusing because imagine that you use a parallelization level like par4, as I am doing here, yes, for this code. But inside this code, you are also calling some library that uses an additional parallelization level, right? So imagine that you request a 4 cores for solving this loop, but inside this function, you are also calling some external library that you activated with some variable, right? So in that case, you will be using more resources than you are located. And that's why I mentioned, and this is useful, right? So that we have some tools in our centers, either top, htop, or this job usage at HPC2N, so that you can monitor the usage of resources. Yeah? If you underuse or overuse the resources. So in MATLAB, there are several ways to over exceed the resources or oversubscribe the resources, and this is just one of them. So in MATLAB, one uses several add-ons or external libraries, and this is one of them, Cplex. Yeah. And imagine that you call a solver from Cplex inside the par4 loop. Yeah. And this one in particular uses the so-called opportunistic approach, where one tries to use all the resources that are available on the machine. So if you don't pay attention to the manual for your solver or your add-on package, then you can easily overexceed the resources. So in the case of Matlab for shared memory, you can use the SPMD, but starting from the 2020 version, there is a nice feature that is called thread pool, where one can use the threads to share some memory, and this results in a faster code. Dynamic programming is more in the direction of par4 and parfeval because one doesn't need to share the memory, but one exchanges memory across the workers, right? And this is more in line of the MPI approach, if you know already MPI. And here is something that you can solve by using the par pool approach that I mentioned with the par4 or par eval or even par sim options in MATLAB. So big data, so if you have a large data, then in MATLAB there are several features like tall arrays or distributed arrays that can assist you in this task, and they work quite well. So this is an example, a demo. Let me see how I am with my time. So it seems that I am okay. Yeah. So I will go with this demo. Yes, and I hope that you can get the basic idea of how parallel computing works. I don't expect you to master this level because first you will need a serial code that is working, yeah. And also, I would recommend that when you write your serial code, you try to document that and write that in a clear manner, right? So that later on you can read easily through the code, right? Because when you add a parallelization layer, the problems that you have in the serial mode, yes, are somehow magnified. Yeah. So, for instance, if you have some issues with the path, setting the path in Matlab, sometimes it's not straightforward to set the path or to declare some variables, right? Then these issues will be magnified completely when you try to run in parallel mode. So that's why I recommend to start with a working code in serial mode that gives you the answer that you want, the correct answer, right? Also, you try to document the code, write it in a way that not only you can understand, but also your possible developers. And this can help you considerably in your development of the code. Yeah? So here there is an example that we have seen several times. It's just a loop, for loop. And here we have some iterations. This is in agnostic language as agnostic. And it has only 4 iterations. Here I have a function called wait, which will wait for 1 second. And the purpose of this will be to simulate some workload for 1 second. So in order to avoid any extra code, I wrote some simple wait function. But this is the part where I have seen in several codes from researchers, right? That people write a long list of functions that are executed many times within a big for loop. And this is something that we can try to avoid, right? So instead of writing a big for loop, we can divide the code into different functions and then monitor where is the part of the code that can be parallelized and that can that where the most of the time is spent, because not not all the code in general can be parallelized nicely. Yeah. So locate the part of the code that needs to be parallelized and can be parallelized. So then, if you execute this loop in Matlab, then we can see this behavior in one CPU. We can see that it takes 4 seconds because there are 4 iterations, yes, of 1 second each. But if we parallelize this code, then we can reduce the time. And if we use 4 CPUs, then the simulation time will be divided by 1/4. So here there is an example on how to run, on how to set this code. So this is the part that was most likely confusing in the previous lecture. And here I will use the batch option in Matlab, in the Matlab GUI. So that's why I don't need to write a batch script. And because it doesn't take a long time, right? And I can fetch the outputs directly, then I can use this. So I can use the par cluster Kebnekaise, use the number of iterations, and then use the C batch for this function, yes? sleep serial, and also I can use this for this sleep parallel function. And these functions are defined here below. So you can copy and paste this script and execute it, and then take the timings. So I can do this. Let me see if I haven't done it. So here I have the script, and then I don't need to write the batch job for running the sh script on the terminal, but instead I created this handler, and directly on the Matlab GUI, I can submit this. Yeah. So you can see here that it is being submitted to the queue, and these are the arguments that are used, right? And this should be in the queue, and therefore these jobs are not executed on the login node, but they are executed on the Slurm queue. So once it finishes, it will report the times, right? So here there are some exercises where you can see how the code, how one example behaves when you change the number of cores. Yes. And this is just for one example here for an integration 2D. Yeah. And here you will need to modify the file for Matlab and correct these fix me strings, yes, so that it fulfills the instructions here using 1, 2, and 4 workers. And also you can change the grid size in so that you can monitor the behavior of the jobs by using the top command or is job usage at HPC2N. So in the example that I wrote above, you can see that for the serial version, it took 4 seconds, and for the parallel version, 1.666 seconds. So in general, you won't see exactly 1/4, right? Because there is some overhead when you try to parallelize the code. And that's something that you also need to consider because the task that you need to parallelize should be heavy enough, yes, to overcome the initial overhead from the parallelization. So if you are trying to parallelize some simple functions like a root square, which is well optimized in any language, then you won't see any faster code. And instead, you will see that your code runs slower. Yeah. But in order to get some good speed up, then what you put inside the for loop, this should be heavy enough. And this is a bonus point, a bonus exercise that you can try. And this is just for parallelizing a loop workflow, but this is more realistic by using some data frame. Yes. And I would say this can be helpful for more realistic situations that you can face in your research. So this is more advanced and also a bonus exercise. So you can try that and let me know if there is any questions. we can do it until, let me see.